Anyway, well, I hope I don't need to introduce our next speaker. If you don't know, recognize Pat, right, or have seen what he's done for the industry in our space as the architect of WebPageTest.org, then you must have been living under a rock, right? So I'm really, really, really pleased to have Pat here. Just like I say, it's the first time I've been able to introduce Pat on stage. He has done like other previous meetings for London WebPerf. I think when Stephen Thayer was kind of like running the group a long while ago now. But anyway, so I'd just like to give a big round of applause to Pat, and we'll have his talk on prioritization and the web.
Well, thank you. Now I won't be able to live up to that, but that's okay. And to be fair, I mean, when I found out I was coming to London, my first check was to see, is London WebPerf having a meeting that week? Because this is my favorite place to come to when I'm in town. I just don't come to London that often. So it's really exciting to be here. So I'm going to be talking about resource prioritization, fetching, ordering, that kind of stuff. Before recently joining Cloudflare, I was at Google working on Chrome. And I'd say I spent 90% of my time looking at waterfalls going, hey, why is that loading there instead of before? Or should it be loading after? And that's kind of what I did all day. And it will drive you insane. I'll just warn you about that now. I apologize in advance for the really crappy waterfalls I'll be showing you. They were all drawn by hand in PowerPoint. But I want to talk about sort of a hypothetical page for right now to sort of demonstrate why these things are important. And it's going to have two blocking JavaScripts in the head. You've got your actual download time for the JavaScript is the dark yellow, kind of like the waterfalls. And then you've got the pink, which is the parse and execute time. The sizes are arranged so, roughly 600K of JS will take 1 second to download, compressed on a 5 megabit cable connection. These numbers weren't picked randomly. 1 second is really easy to explain and add up when we're talking about these things. And it will, 1 megabyte of JavaScript uncompressed will take 1 second to evaluate and parse on the browser side of things on a reasonably fast device even. So just be warned and when you're looking at things. We also have 2 JSs down at the end of the body. Best practice, put your blocking JS at the end of the body so you're not blocking render. We've got 1 CSS file in the head, 2 foreground images that are in the viewport that the user cares about looking at. And we've got 2 images way down in the viewport that they don't care about looking at necessarily right up front. And we've got our friend, the web font, because what site is complete these days without a web font or 10? And they're really tiny. So we roughly have 9 seconds worth of content to download on a 5 megabit connection. No matter how you carve it up, it's going to take you 9 seconds to get that data down to the browser. That's what the bandwidth allows. That's assuming you're downloading the full speed of the content the full time that you're downloading it. And we have 4 seconds of script parse and eval for the 4 different scripts we've got, all on the CPU, all on the main thread. And we've got ½ a second of layout. So if you add it all up, you've got 13 seconds to load the page. Should that be your load time target? I would hope not, especially since this is only a very simple page with 4 JSs and 4 images. So we're starting out in kind of a bad position here. So the simple model, we've downloaded everything. It's all downloading at the same time. It took us 9 seconds to download our 9 resources. We don't have the font yet. The browser doesn't know about the font until it's done the style and layout, right? So it hasn't discovered the font yet. It parses and evals each one of our blocking JavaScripts in the head. After the JavaScripts have, I guess in this case, we have the style sheet. Yeah, actually, it can't do the layout until it reaches the body of your page. So until it's made it out of the head. So it can't do the ½ second of layout that the CSS triggered until after that. Finally, at 11.5 seconds, we've started to render our page, followed by 2 seconds of parsing for the end of body JavaScript that needs to execute before it gets to DOM content loaded. And right here, we've discovered our text, and we can start displaying our font what is that, 0.1 second after we've rendered the main page. So yeah, so we finished parsing the head here after we've downloaded absolute everything and executed the JavaScript. As far as metrics, if you're tracking metrics, the first paint was 11.5 seconds. Same thing for first contentful paint. If you're not aware of it, first contentful paint is kind of a newish Chrome-driven metric, which is the first time a foreground image or text is painted on the screen. So something other than like a color change of the background. First text paint, which is also exposed by Chrome, 11.6 seconds. That's when the content can actually be read. And DOM content loaded, which I propose is another very interesting metric that you want to track. That's when the full DOM is constructed and sort of the proxy that we've been using for your application is ready to execute and interact with the user. It's 13.5 seconds. On load, also 13.5 seconds. We weren't doing, all the images were already loaded up front. And time to interactive. Anyone heard about that one yet? Okay, good. Chrome team has been pushing that pretty hard. We haven't really figured out what a really good definition for it is, and the definition keeps changing a little bit, but it's basically after the page has rendered, after DOM content has loaded, and after the main thread has gone idle for 5 seconds to give the user enough time so that they can expect the page to be responsive when they try and click on things. Whether or not that makes sense to you as an application, the one thing to watch out for, the definition for time to interactive does not really count scrolling as a page interaction. So you might not actually care about TTI if your main consumption model is consuming content. You're looking at something, scrolling, reading content. Time to interactive may matter a lot less because you can almost always scroll a page these days, unless you've got really nasty scroll handlers. While we were doing this, while we were downloading the 9 seconds of content, the CPU was completely idle. Then while we were actually dealing with the downloaded content, the network was completely idle for the last, 5 seconds of loading the content. So this is where ordering starts to matter. You know, when everyone's special, nobody is. Downloading everything at the same time, it took us 9 seconds to download everything. We didn't have anything ready earlier. And so what we can do is if we order things so that the critical stuff is serialized, just the things that we need to render the initial part of the content. We know we need the style sheet first. It's before the JS. The JS can't execute until the style sheet has loaded. So we'll go ahead and load that first. Then we'll load the first JS file that's blocking in the head. Won't do anything else while that's downloading. While that one's parsing, we can interleave and download the second JS file that we're going to need when the first one's done executing, and start interleaving the CPU and network. And here we've got, okay, both of the JavaScripts have finished loading at 3 seconds, finished parsing an eval, and we've made it out of the head at 4 seconds now instead of, 13 seconds, something like that. Oh, sorry, 11 seconds. And we can do the layout. And we have, all of a sudden, we've got our first paint down to 4.5 seconds by rearranging the order that we're downloading these things in. And the first paint, now we've got the text visible that the user can start consuming. So here at first paint, we haven't shown them any images. They don't really have any content. They've gotten like maybe a background color change or something like that. Here they can start reading your headline, your story, whatever you've got attached to your custom web font. If we preload the font using a link rel preload header, we can tell the browser about the font that it's going to need and say, hey, you're going to need this by the time you get to layout, so we can start interleaving that with the JavaScript execution. Because now the network's idle, it's just doing CPU stuff. We can preload the font and have it ready by the time it does layout. And so now all of a sudden we've got the text displaying at 4.5 seconds as well. You know, in the grand scheme of things, 4.5, 4.6 seconds doesn't make a whole lot of difference. When you've got 10 web fonts, it starts to make a little more of a difference. Yeah, so that's the link rel preload spec. The slides, don't bother. So you can take pictures if you want. We're going to share the slides afterwards as well, so you'll have links to everything. And now we've got, okay, so this is where things start to get a little religious, and Cornell will probably tackle me on stage at some point. But so now we're running the end of body.js while we're still doing the parsing for the scripts above the head, and interleave them just like we did with the earlier. And then we start loading the images. And so this one, if you're optimizing for time to interactive, you want to get all of your JavaScript out of the way and executed quickly. So we've got all of the DOM content loaded, and all of the script parsing is done by 6.1 seconds. So we've pulled our time to interactive way in, but we still don't have any images visible to the user. We started downloading those after the JavaScript files. And so that's where we start the religious wars. Are your images more important than your time to interactive? Speed index versus TTI basically is what it comes down to. Luckily, I don't need Cornell to beat me up. I'm sort of a same fan. I think the visual experience is a lot more than the execution, because they're more likely to take a look at your page, consume it, pause for a second while they're looking at what's loaded before they actually try clicking on anything. So you have that little bit of time between when the viewport at least is loaded and when they try to interact with the page to sort of make up for the difference. And so priority hints, new spec coming out. I don't think any of Chrome may have implemented it. I don't know if they've actually shipped it to stable yet, where you can say importance equals high or low. There's also, I think there's like a medium or something, which is basically the default it would have done normally, which you can say basically boost the priority of this resource higher than you normally would, or lower the priority of this resource than you normally would. And for that, so what I probably didn't cover, one of the things Chrome, and this is Chrome specific, that it does once a page is laid out, if it discovers images are visible in the viewport, it gives them a much higher priority than images that are below the viewport. So it will try and load visible images sooner, but it won't know about that until after it's done layout and discovered that they're in the viewport. What you can do here is you can say, these are my hero images. These are going to be in the viewport by the time you do layout. So start loading them sooner. And so we can start loading the critical images before we've done the layout. And if you're doing progressive JPEGs, by the time you actually do the paint, you've got 3/4 of the images loaded. And so basically they look visually complete as far as byte-wise would go. And then we'll go ahead and download. And so in this case, I'm actually also downloading them in parallel instead of staggered one after the other. So you have them both loading partially at the same time. This is where things get dicey and where you really want to pay attention to things. For JavaScript and CSS, in order, full bandwidth for each resource one at a time is the best model. You want to download an entire JavaScript file so that you can parse and execute it while you're downloading the next one. Sort of like when we looked at the first slide, if you're downloading all of your JavaScript all at the same time, then none of them are special. You have to wait until they're all downloaded, and then everyone's scrambling to race on the CPU. When you get to images, if you've got progressive JPEGs, for example, downloading them concurrently is a better model than downloading them one after the other. And so you kind of want this hybrid where all of your code is staggered, but then all of your images download concurrently, sharing bandwidth, so you can get sort of that progressive delivery on the images. And so the priority hints works the other way as well. You can boost the priority of things that would normally be high priority. You can also lower the priority of things. The main place that comes into play is with like either end of body JavaScript, where you want to lower it to say, no, delay that until afterwards. The other main one is, at least in Chrome, is Async JS. Whenever you put an async tag on JS, it will treat it a fairly low priority. I think it gives it the same priority as invisible images, because it's like, yeah, these are kind of load whenever you want JS files. We won't load them critically. If you do your analytics tag or an async version of like Google Tag Manager, for example, and you load your script too late, you might start losing your page views. And this is one of those sort of balancing acts between business and user experience. And so if you put an async tag or an async marker on your JS for your analytics, you actually may want to have the browser load that as soon as possible, just not block execution on a bunch of other stuff. And that's where you kind of want to defer from what the browser's normal prioritization would be. So you could say, hey, this is async, but the importance is high. So load it quickly, but don't block anything else on it. So this all comes to play largely in HTTP2. Not sure who's familiar with the HTTP2 prioritization scheme. It was, yeah, Andy's very familiar with it. It was developed by sadists in a room. They all got together. So Speedy, before HTTP2, had a prioritization scheme that included was basically a single number from 0 to 255, where the browser would say, this is the priority of this resource. Do with it what you will. My feeling is, in an effort to diverge from Speedy, because we had to do something different to put our stamp on it, the committee decided we needed a full tree for the browser to be able to spec out a full dependency tree of this resource depends on this other resource, but we also need to be able to download multiple resources at the same time, so each one has a weight for, like, if it's weight 12 and weight 4, the 12 gets 3/4 of the bandwidth, the 4 gets 1/4 of the bandwidth, but they're downloading in parallel, but only after C, which had a weight of 8, but it was sort of at the same level of this other item. And to top it all off, there's also an exclusive bit that you can set on any one of these, which says, download this without anything else downloading. So stop the downloading of everything else if you're going to be downloading this. So they come up with this really nice tree structure that nobody could figure out how to actually implement. So this is red pill, blue pill time. If you're happy in general with life and the web, go drink some more beer. Unfortunately, breaking you out of the bubble, you won't be able to unsee how broken things are. And it's been keeping me up at night. I mean, I was happy in my Chrome bubble before I left the Chrome browser and started looking at the real world. So browsers, how you doing with performance? It turns out not so well. Chrome, this is what a dependency tree looks like for Chrome. This is one of my, I think it was like my wife's blog that I copied over. And so HTTP2 works best when you've got all of your resources on your page coming through one connection. That's the only way resources can get prioritized against each other. So the browsers in HTTP1 land used to do prioritization on the client side, and they would decide what order to fetch resources in. And that's how they would prioritize what should get delivered first or not. When HTTP2 came along, as Speedy, being developed at a company where, you know, basically one server delivers your entire page. And granted, your Google search page is like 3 resources. But anyway, the prioritization of the resources was deferred to the server. And basically now the client can build this whole tree model, make all of the requests to the server and say, you know what? This is everything I know about that I need. This is how you should deliver it to me. Follow this magical tree, and I will be really happy. And then the server starts prioritizing the resources that it has available and trying to deliver it in the order that the browser asked for. So Chrome builds a tree out. Every resource is always marked as exclusive in Chrome. Whether it be an image, a script, a CSS file, whatever, it's largely because of a separation of knowledge in the networking stack versus the renderer. The networking stack knows nothing about what the types of resources are. It just knows, even worse than a priority number between 0 and 255, the networking stack sees a priority between 1 and 5. Chrome has 5 internal priorities. Those are all that the networking stack sees with the requests. And it goes from that, and it tries to build a tree. And so what it does is, as the requests come in, if it's a lower priority than something that it's already gotten, it just builds a serial list. And it goes, OK, this was a 220 priority. It'll start out my list. Oh, another 220, 220, 220. They're all either equal to or lower priority than something that came before. I'll just add it to the queue of requests that I've got, all downloading serially because everything's exclusive. We get some JavaScript. We get some images. We're coming along. You know, say maybe here where we're working on the queue now has, we're an image. The last thing that we've added to it is a weight of 147. And all of a sudden, we get a really high priority CSS file, for example. And it goes, oh, crap, I can't add that to the end of that tree. I'll start a new queue. And the new queue starts at a weight of 256. And now we've got sort of two queues we're building. It'll continue to add to the other one if it has lower priority requests. And so as newer high priority requests are discovered, they basically start new queues in Chrome, everything marked as exclusive. The assumptions on the Chrome side of things were that as the server is working its way through each layer, basically from the root, it'll go, okay, what's the highest priority thing at the head of a queue that I know of right now? Send that. And so by the time it gets down to the lower priority resources being at the front of the queue, it can go pick off from another queue where it knows about higher priority resources. So in theory, it'll deliver everything in the order that the browser asked for, from highest priority to lowest. All blocking, all one at a time. So no concurrency across your images, for example. I say in theory because that also assumes that the server is honoring what the browser asked for, which may or may not always be the case. Firefox went whole hog with this HTTP2 tree structure. And so they looked at the model and went, you know what? We're going to build ourselves a virtual tree that goes, these resources should all download concurrently, but they should all follow this other set of resources. So they have a static set of nodes, which they're basically virtual streams in the HTTP2 connection where it has no request that's attached to them, but they use them as placeholders for grouping of the resources. And so they've got urgent resources, which are basically the HTML, and they get the highest weight. And so we have the weights for the virtual groups, which basically says anything that's in the leader group gets twice the bandwidth of anything that's in the other group. It doesn't download exclusively from each other, so you've got these sharing, but everything in this group gets twice the bandwidth of everything in this group. And then within this group, all of the leader resources, they split bandwidth. They get the same weight, so all of your CSS is downloading concurrently, for example. But then we have this follower group, which has a weight of 0, which basically means the leader, you dedicate all of your bandwidth to these files here. When they're done, drop into the follower group, and then the 200 weight of the leader group gets everything that's in this follower group, while still taking half of your bandwidth for everything that's in the other group. So the JavaScript is still taking like 1/3 of your available bandwidth. Then CSS is taking 2/3 of it until it's downloaded, and then it splits the remaining bandwidth between images and fonts. So you have sort of this complicated model of what gets downloaded when, but within any group, everything's downloading all at the same time. And so you've got your images, it's great. You've got your progressive images downloading concurrently, but your JS and your CSS are not. They are downloading concurrently, it's just not great. And you've got your CSS and JS basically splitting 2/3, 1/3 for the bandwidth. So good, bad, I don't know, it could go either way. It's good for images, not so great for JS and CSS. It's a pain in the ass to understand why your resources are downloading in whatever order they are in practice. Safari. As best as I can tell, they took the code. So several years ago, Chrome forked WebKit and made Blink. The priorities that are in Blink right now are what came from Safari, from WebKit before Chrome forked. This is what Chrome used to look like when it was doing Speedy as well. It basically takes the internal priority of a 1 through 5, and it maps it to a static number, and that's basically the weight. It made a lot of sense in Speedy, which basically said, hey, these are high priority or these are low priority. It makes less sense in HTTP2, where everything is hung off of the root, and it gets a weight that's based on whatever the priority is. So everything downloads all at the same time. You get a little more priority for CSS, gets more of the bandwidth than JavaScript, for example, and then fonts, and then images. So your CSS, or actually CSS and JS get the same. They get like 3 times the bandwidth of your images allocated to all of them. But everything downloads all at the same time, just with varying differences on the bandwidth Edge, i.e. Well, I guess as of today, that might change, but it doesn't support prioritization at all. So everything downloads all at the same time, all with bandwidth split equally among everything. So your critical, this is basically the first slide that we started out with. In case anyone thought it was completely hypothetical, that's actually Edge and IE's download model. Largely, my guess is the networking stack for Edge is actually deep within Windows, and Edge has no interface for telling the networking stack what the priority of resources are. It only has a way to say, hey, fetch this URL. And so by the separation of layers, there's no way to build a complicated priority tree. So what you get is all of your resources downloading all at the same time. What do you do about it? They're browsers. Convince all of your users to use different browsers, better browsers. If you are testing all of your testing on Chrome, stop. Try testing in some of the other browsers. I definitely at least recommend Safari. You're going to have a lot of iOS users. Don't do mobile emulation for all of your testing because Chrome's rendering engine and download networking order is very different than real iOS, real Safari. So do some testing on real devices using the real browsers that your users are using, because the prioritization order is going to be very different. You can order things in the HTML, roughly in the order that you'd like to get them downloaded in. At the end of the day, all of the browsers still send out the requests in the order that they're discovered. So you'll still see requests for the images in the order that the images are defined in the HTML, even if they're all given the same weight. At least you'll still get some level of ordering information in there. Anything that's hidden, that's critical, your fonts are sort of the key use case for this, but you've also got, if you're using a tag manager that's inserting JavaScript or something else that's written in background images, CSS background images aren't discovered until after layout. Priority hints or preload hints to say, hey, load this resource, you're going to need it, so that it can discover it earlier. This one's a little more controversial. I think Cornell's also famous for saying, don't try and race the browser. You can't load images faster than if you define them in the HTML and let the browser load all of them. The converse is also true. The browser is going to find everything that you don't want it to load, and it's going to request those at the same time. So it might make sense to lazy load images that are below the fold after all of the above the fold images have loaded, for example. You have to be a little careful because you still want them to be discoverable by crawlers and all of that kind of stuff. But given the Safari model, to some extent Firefox, and the Edge model of everything downloading at the same time, if you can prevent the browser from knowing about something, you can at least get some level of scheduling there where you go, hey, these below the fold images are less critical. And once I get DOM content loaded and my above the viewport images have loaded, then let the browser discover them and figure out whatever it's going to do after the fact. As best as I can tell, these are sort of the only knobs you have on the client side for being able to control the insane situation that is browser prioritization. So servers, woohoo! All HTTP servers support prioritization. So we've got that going for us, right? If anyone's still questioning whether or not they took the red or the blue pill, now would be a good time to leave. Maybe not. So the first thing I worked on when I got to Cloudflare was I wanted to make Google fonts faster. They're in like 65% of the web pages. I've got strong feelings about fonts. That didn't make me very happy. Google Fonts in particular has this insane, sorry for everyone on the video stream, this is now recorded, but it's insane. You load a CSS file from a third-party resource. So you've got to do the DNS lookup, socket connect, TLS negotiation, fetch the CSS, which blocks all of your render for loading the CSS file that defines the fonts that you're going to use. And then when the font's discovered, it has to do the DNS connect, socket connect, TLS negotiation, and fetch of the font because it's served on a completely different static domain from the Google font CSS. So you've got 8 round trips to download a font file for the text that hopefully the users come to consume. One of the first things I did was try and do a thing where I'll inline the CSS from the browser-specific CSS, because of course they UA sniff. Do what I tell you not what I do, right? So they UA sniff to figure out which CSS file to send you for the browser that you're using. So I inline the CSS directly in your HTML. So we get rid of the 4 round trips to fetch the CSS. And potentially also, I proxy the font file itself. So it comes from the same origin as your page. So now you're also not having to open up a separate connection. And in theory, you can prioritize the font against the rest of your resources. And you can delay the images and not split bandwidth and deliver the font files quickly. And so I rolled it out. I tried doing some testing. And my fonts, instead of loading at, what was it, 2 seconds, it took 5 seconds to load the fonts. You can imagine that's a little demoralizing when you've got this great idea and you're like, I can fix the web. I'll get rid of all of these round trips. And all of a sudden, I made it orders of magnitude worse. There's a really long, detailed blog post on the Cloudflare blog about why that is. But it ends up, we largely use Nginx, has great HTTP2 prioritization in the code. Actually getting HTTP2 prioritization working in production is a whole different nightmare. There are buffers everywhere on the network and in your servers. So in our case, we had 5 megabyte TCP send buffers, which is great for server scaling. The server's not sitting there spinning, trying to send data, because it can just put it all in the send buffer and let the networking stack figure out about delivering it to the client. The problem with large send buffers, or buffers in general for HTTP2, is so font files are discovered late, right? We talked about how they're discovered during layout. So all of the JS and images have already been requested from your server. Your page goes, hey, I need this font file. Really, really critically, top priority, send it to the server. Server already knows about all of your images and everything else. It dumped 5 megabytes worth of images into your send buffers. And then it gets that critical font and goes, that's nice. I'll add it to the end of the 5 megabyte buffer. And so you've got to get 5 megabytes worth of data before you can get to the font. And so one of the critical things to get HTTP2 working and prioritization working is you need to have the minimal amount of data in flight to the browser so that the server can actually respond to prioritization quickly and reschedule things and jump ahead in the queue. And so for our case, at least, I was fairly lucky. There's a Linux kernel setting, TCP not sent low watt, which basically says use, in the case that I did at 16K, allocate 16K of TCP send buffer atop whatever you need to fill the connection, to keep the connection full and not sort of starve the connection, to be able to keep it going very well. And so that solved our case. The other case of network buffering introduces one where you don't have a whole lot of control over. And this is also our friend buffer bloat. Networking devices somewhere along the path, probably at your cable company or your cell head end, wherever your bandwidth goes from really fast to really slow, usually at the ISP. They've got a whole bunch of buffers where they buffer up the data before they're going to send it further down. Most congestion control, TCP congestion control before BBR, basically, any loss-based congestion control waits until it detects that a packet was lost before it goes, hey, okay, the buffers are full, maybe I should use smaller network buffers. And so what it'll do, if you've got a 5 megabyte buffer in the network, it'll send 5 megabytes of data without losing any packets. They're all getting queued up, eventually act. And so you basically have effectively the send buffer, it's just in the network. BBR, which basically on Linux is these two syscontrols to turn on. What it does, instead of waiting until a packet gets lost, it watches the time for the ACKs to see how long did it take this packet to get delivered. And once it looks like packets are taking a little longer to get delivered, it goes, ooh, you know what? I bet I started hitting network buffering. Let me scale back how much I'm sending. So it tries and fills the pipe just with enough data to keep the pipe flowing at full speed without buffering. And so you need to enable BBR or something like BBR to be able to keep network buffers out of your path. think. Yeah, and so that's not all of the buffers. There's buffers everywhere. I think I was looking through like the Nginx settings to see, okay, we've got these buffers we fixed. What other buffers do we have? There are read buffers, write buffers, proxy buffers, for how many internal buffers you're using within the server product. You have to tune them all basically to try and minimize as much data. And it's one of those trade-offs where you don't want to overload your server spinning in a really tight loop, sending 1 byte of data at a time, but you also don't want to send 5 megabytes and fill up buffers and cause these issues. Otherwise, HTTP2 breaks. When you're looking at a waterfall, the easiest way, and this is actually a real waterfall of that page that I was showing you earlier, when you see critical resources like your CSS, JS, your fonts, all getting downloaded well after your images, you might have a problem. And that's kind of the main thing to watch out for. Recently, WebPageTest, right about August, when I found this and started trying to figure this out, the waterfalls changed a little bit. And instead of, they used to send basically a really long download bar from when the first byte came back until it finished, you'd have a completely opaque bar where it's like, why did it take 10 seconds to download that 10K file? It's been changed in August or so where you get tiny slivers in the download bar now for when it's actually downloading bytes for that resource. So you'll get like, I don't see it in here, but you'll usually get like a really thin line towards the beginning when the headers arrive, and then you'll have really long gaps, and then you'll start getting more data when the actual bytes for that resource are being downloaded. Because most of the web servers these days will, regardless of whatever prioritization is available, they'll send the response headers for a resource immediately, and then they'll prioritize the actual data delivery. And so you'll be able to see how, in this case, like things are pretty much honoring the Chrome exclusive flag, so it's only downloading one of them at a time. You'll be able to see, hey, is it interleaving data between multiple requests, that kind of thing. Yeah, so pretty much the same thing. Chrome's loading is basically a 2-phase loader. It's the only browser that does it. While it's still in the head of your document, it's going to delay low priority requests. So it's not even going to request images for the most part. It'll request one low priority resource at a time, but it's not going to request the bulk of the images until it gets out of your head. So most of your waterfalls for Chrome are basically going to have what look like 2 steps. The first part of your waterfall is it's downloading what it thinks are the critical resources in the head of your document. And then you're going to get to the page where it opens up the floodgates and downloads everything else that it thinks, okay, I'm through with my critical resources now. That downloading the rest of the things is usually where you'll see priority problems in Chrome, just because usually stuff in the head is already critical and you won't notice small differences with the ordering of those. But when you get like your end of body JS being, or your fonts in this case, lots of fonts here, being delayed by images elsewhere on the page, that's where you'll start to see the problems get exposed. As far as the metrics, your first text paint, DOM content loaded is a fairly big metric that's going to get pushed out if your high priority JavaScript is getting blocked by the images, because the images are not going to affect DOM content loaded, but your JavaScript is. So if you're looking for metrics that move based on the prioritization work or not, DOM content loaded and first paint are pretty much the 2 big ones. So now that we know servers can go wrong and Cloudflare's was wrong until August or so, how are things doing? There's a test page up on GitHub that you can install on your server. It's meant to exercise Chrome's prioritization in a specific way. Let's see if I talk, yeah, to trigger high priority resources getting downloaded after 3 megs of low priority resources are already requested. So it basically has one blocking script in the head in order to delay execution and discovery of other resources. It's got 30 images laid in the body that are all really low priority, but really easy for the browser to discover and request right away. And then it's got one web font and one background image. Both of those only get triggered once layout happens, so once it's gotten out of the head. And then there's a visible image in the viewport that's added by JavaScript that executes after the blocking JavaScript. And it has a document right at the end of the body that inserts another blocking JavaScript. So all four of these resources get a really high priority because they're blocking or they're visible images. And if things aren't working well, so this is sort of what the priority tree ends up looking like. You'll get the one fork of the tree, which is all the low priority resources. And then the late discovered really high priority resources get a sort of separate fork in the Chrome tree. Don't optimize the page. It's really easy to build the page so it loads faster. You want to load it exactly like it is because it's designed to load in Chrome in such a way to exercise your server. It's also designed for Chrome specifically. So testing it in Firefox, where it's going to request everything, all with different weights, it's not going to get the same sort of exercise of things loading serially and exclusively. And Firefox also doesn't have the visible image, gets a higher priority sort of exposure. If you test on a 3G connection, it exposes the issues much more clearly. And sort of a pet peeve of mine, if you can avoid it, never, ever, ever use Chrome DevTools 3G shaping inside of DevTools. Chrome's traffic shaping is all done inside of the browser after the network requests have actually arrived inside of the browser. And it's just throttling the speed at which it feeds it to the rendering engine. That won't tell you anything about how your network's actually behaving or how the H2 push is sort of the other thing that it's really broken for. But in this case, since it's done at the DevTools level, not at the packet level, you won't get to see things like network buffering and everything else because it's going to suck all of the network bytes in as quickly as it can. And then a good waterfall is you'll have sort of all of the requests. And then these at the bottom of the waterfall are your really high priority things that were delivered late. When it's working well, those will be requested late, but they'll be delivered really, really quickly because they were given really high priority. And you'll still get all of these other images downloading much later. When it's not working well, they'll tend to usually either all of them or two of them will end up taking pretty much the whole 20 seconds in this case to download. And it should be fairly clear in the waterfall. You're going to have bars down at the bottom of the waterfall that stretch way out and are loading way later than they should normally. Visually in the film strip, since the visible image is one of the things that sort of gets late discovered and high priority, when it's working well, you should get a film strip which in around 4 seconds, it's visually complete, your page is finished loading. When it's not working well, it's 20 seconds. So the visual experience should demonstrate it very well to like an ops team, for example, of why they need to look and fix it. Because the difference between 4 and 20 seconds is pretty freaking huge. Andy Davies also set up a GitHub page. So tracking the state of the world. I wouldn't necessarily recommend posting, if you're running your own edge, and where most of this matters is whatever the browser is talking to, that's where the HTTP2 prioritization needs to be supported and done well. So if you've got a CDN, that's the thing that the browser's talking to, that's where your prioritization needs to be done well. If it's talking to a load balancer, it's your load balancer that matters, not your servers behind it. I wouldn't really recommend tracking how well does Nginx support prioritization, because that's going to depend on your deployment, right? What your TCP buffers are configured for, or what congestion control you're using. If you're using a service where it's either a hosting provider, a CDN, a load balancer device, run the tests, submit an issue with your test results, and we'll be able to tell if it passed or failed, and we'll add it to a table so we can track what works, what doesn't. I mean, to give you an idea of the scope of things, we've only found 2 to 3 implementations on the web so far that actually work. Google's Edge servers do not prioritize correctly. They invented Speedy and HTTP2. Odds are yours don't as well. So I highly recommend testing it. It's a huge deal. If you don't fix it, what you're going to end up doing is you're going to migrate from HTTP to HTTPS and HTTP2. You're going to do testing, and you're going to go, it's slower. Why is it slower? We're going to go back and we're not going to do HTTPS. And it's not because HTTP2 is slower. It's because prioritization is not working correctly. And so you're going to come to wrong conclusions. You're going to roll back, or you're going to spend a whole lot of time trying to figure out dev work for what's really a production configuration to get prioritization actually working in the wild. What do you do about it? Hopefully, we're trying to do that with the tracker. We need to try, for the benefit of the web, for HTTP2 to work, we need it to actually work in the wild across the web. Otherwise, people aren't going to use it. HTTP3, quick, has all the same problems. All you're really doing with quick, it uses the same prioritization scheme as HTTP2. You're moving the congestion control and the TCP buffering into the application layer instead of the network. But you're still basically going to be depending on every server doing the buffering correctly or doing the congestion control correctly. So none of this is going away with quick. Quick is enough years down the road in practice anyway, that you're not going to want to wait for that to happen. So test, fix your servers. As far as what you can do for the browsers, pray, hope, ask. Maybe the browsers will eventually get to the point where they're migrating off. Your best bet is to try and schedule your resources in an order that makes sense, so that even if it's requesting everything at the same time, you're still getting most of your visible content as quickly as possible. Hide the stuff that you don't want it to know about. Test on the browsers that your users are actually using, because it's going to make a huge difference. That's largely it for me. We can do some.
Right, questions?
It's Imran here. Where do bundle creators like Webpack and the dependency graph of those tools fit in this picture?
So Webpack and its dependency graph and the bundling and everything that it does is largely to take, you have like hundreds of imports in your dev version of your JS. It'll do the tree shaking and everything to figure out what code is actually needed. And that'll be the 1.js or 2 or 3 JS files that get loaded by the page. That just ends up being a blocking script in the head of your document for the most part, which then gets prioritized by the browser as the fact that it's a blocking script in the head of the document. And then whatever modules that get lazy loaded later are usually loaded by code later. So the browser doesn't even know about them. They're relatively hidden. Not a lot you can do about it other than those will be given a high priority. You'll want to watch out. They'll probably be competing with other lower priority things. One of the things that I didn't mention is third parties and CDN or static content sharding and things like that. HTTP2 really needs everything to be on the same connection to be able to prioritize. If you're fetching things from a static file CDN, those are going to be on a separate connection. They don't get prioritized against things that are on your main connection, for example. And so they'll be competing with bandwidth, and they'll be in sort of the download everything at the same time mode. Same goes for third parties. Those are on other domains. There's sort of an escape hatch for HTTP2, where if the DNS records point to the same server IP address and the cert is shared, then it will reuse your existing connection for the sharded domain. There's a lot of hoops for that to work right, and it still needs to do the DNS lookup. So serve everything if you can from your same domain as your origin. We're well past the days where you need to shard. So like all of your Webpack.js, for example, make sure it's coming from the same domain as your HTML and as your images and everything else. So it can at least be prioritized against everything else to the extent that things are actually prioritized. It's about all you can do.
Anyone else?
Oh, yeah. So we recently turned on H2, and we're having all these problems. So it's slower in pretty much all instances. Now, I've raised a ticket with Fastly to fix this issue, I'm hoping. Now, if that doesn't improve, I think we're going to have to roll back. Is this something that you've seen people do? I just want to know if maybe it's a question to the room as well.
Yes, Human, standing by the corner in the back, is one of the engineering leads for Fastly. But Kazuo, and also, yeah, we have a bright red shirt up front, Fastly. Probably the wrong choice in colors for wear because you're too easily identified. But so Kazuo, who built H2O, which is sort of the gold standard for HTTP2 implementations, and he's been dealing with all of these buffer things forever. There's some edge case somewhere that's getting exercised, and they're all over it. They're on top of it. They'll get it figured out, I expect, really quickly, because it is their strong suit, and it's definitely Kazuho's strong suit and pet peeve.
Hang on, Peter. Just one sec.
I'll start from scratch. Can I just add one thing? I don't know your particular situation, but there isn't 100% possibility that what you're noticing is because of this issue. H2 has lots of problems, and we've gone around for years now saying that it's not the silver bullet everybody kind of thinks it is. There's lots of things that could be happening because of whatever the app looks like or whatever is happening on the network. If there's any packet loss, you have TCP header line blocking issues that are exposed. That's going to slow things down. We have data about this. Congestion control. There's all sorts of stuff that could be happening. So it could be because of this, or it could be because of any other number of issues that H2 has. I will tell you this, though. You're not alone in finding that a transition to H2. And that's not just with Fastly. I'm talking across the board. That a transition to H2 is not like the panacea that you imagine it would be. We constantly keep hearing stories, both pro and con. Like the opposite of this is I had a customer come to me at a conference say, we went to H2, it's amazing. We are orders of magnitude better than before. I'm like, great, write about it, because we keep hearing these other stories and we'd like to balance them out. So in your case, and again, I don't know what your case is. It could be any number of things, including this, or any number of things that are problematic to H2 inherently. There's a reason that Quick is like the new kid on the block, and we had the Quick thing here not so long ago. That there's a reason that that's happening is because we did well with H2, we moved on, but there's still a lot of work to do, clearly. So it could be any number of reasons that it's happening. This is not the thing that's broken with H2. There's lots of things that are not there with H2. That's all.
Yeah, and so we talked about the broken state of browser prioritization, for example. Depending on where you're getting your data from, and if it's from real browsers, it's not entirely out of question that Safari is going to be slower no matter what you do, just because of how it's requesting the resources, for example. It could also be, it depends on looking at the waterfall and like micromanaging and looking, is it a priority inversion or is something else going on? Is it domain sharding and all of a sudden things can't get prioritized against each other, third parties? There's all sorts of really weird crap that goes on. Chrome in particular also has so Chrome has a client-side resource scheduling logic that it applies, and sort of the two-phase loading we talked about. For the longest time, it turned all of that off when it was doing HTTP2. And so it wouldn't even do the two-phase loading. It would send all of the requests up immediately as soon as it knew about them, even while it was still in the head. And then if prioritization wasn't working right, you'd have even bigger problems with Chrome. Chrome 70 accidentally turned that off because of where they moved logic. And so now the part that does the two-phase loading doesn't know anything if the server is HTTP2 or not. So watch this space. It's changing fairly frequently. But yeah, I'd say work with the teams that you're already working on to look at detailed captures of the site to try and identify what the problems are. Are they application problems? Are they protocol level problems? If it's from synthetic tests or from real world. One of the other things to watch out for is when you're doing your synthetic testing, what are the browsers that are being used for those synthetic tests? I will say, though, like Pingdom last time I checked was using Chrome 38 or something. We're on Chrome 70 right now. 38 didn't even support HTTP2. So if you're doing synthetic testing like with Pingdom, for example, you'll be testing HTTPS without any HTTP2 support and getting data that's not useful. You may be running synthetic tests at backbone speeds instead of throttled, and there's a lot in the mix. But good news, it keeps us all employed, right? Because there's lots to do.
Any more? One more. One more.
Regarding priority, with iframes, will the things loading iframe will be low priority or will be competing directly with your home page?
So priorities of things in iframes, it depends. So when they get to the networking stack only knows about the server. It doesn't necessarily know about the iframe or not. And so they're all going to go over the same connection, and they're going to get prioritized against each other. Chrome had an experiment where they would lower all of the requests for iframes. They called it low priority iframes. Part of the war against ads, I guess, or everything iframes. It ended up not going well because there's a lot of content in iframes that people cared about, so I don't think it ever went anywhere. So anything that's loading in an iframe is largely going to compete against your main page resources. The only thing that Chrome does with iframes, especially right now, is it throttles the timers, so they run at a lower resolution. But odds are, if you're loading stuff in an iframe and they're ads, they're not coming from your origin. So not only are they going to compete against your resources, they're going to be on a different connection and not prioritized well against your HTTP2 resources. So they're going to be competing with bandwidth. And they're going to be running in parallel because they're not going to get prioritized. So they'll kind of jump ahead of the priority queue and be competing against everything that you care about. And that's sort of why the HTTP2 model of everything being on the same connection looked great for the Googles and Facebooks of the world, where one server controls all of the content. When we're in the world where you've got 50 domains serving the content that ends up on your page, and none of that can get prioritized against each other because they're all on different connections. Yeah, that guy in the middle. Not a whole lot you can do about it, unfortunately, other than scheduling when you load the iframe.
Okay,
right.
right. I think
Thanks.
we need to say one more huge thank you to Pat.